Hello. Today we're going to talk about linear momentum. So it's a small p. Okay. So linear momentum, small p, is defined as mass times velocity. So this is the vector. It is the vector. And the unit is kg, meter per second, just like that. Okay. So when you speak of a momentum, let's say if this mass is going this way with a mass of 1 kilogram and velocity equal to 1 meter per second, then this means that this mass has a momentum that's going this way, and the p is equal to 1 kilogram meter per second, and it's going to the east. Okay. Now, the relationship to force, relationship of p, small p, okay, small p, to net force. So net force, we're just going to write like that, and we may, just write like that for now, okay? So it's equal to the delta P, delta T, all right? So this is what the physicists found. So this is equal to P2 minus P1, and then T2 minus T1, okay? And then, so we'll put the MV in there. So this is equal to M V2 minus M V1, okay? For the P2 and P1. This is T2 minus T1. So then this is equal to M delta V. So V2 minus V1 is delta V, and then delta T. All right? So that's what we found. I'm going to change in color here to make it a little more clear. So we have found the F, it's equal to M delta V delta T. And that's equal to M A, you see? Okay, so this definition of this relationship, if you expand it out, when the mass is constant, right? So this here means the mass is constant, which is normally true. Mass is constant, then actually become Newton's second law. Okay, so this gets us back to Newton's second law. Newton's second law. All right, so we're going to continue to conservation of linear momentum. So we're going to talk about if I have a mass that's going this way, so M1, V1, and I have another mass that's going this way, for example, V2, and this is M2, okay? And they are on surface, and the mu is equal to 0. So right now, you do have mg and normal force, but they cancel out. So right now, the summation of the forces, all the net force, it's equal to 0 because your mu is equal to 0. So, and the system, okay, so be careful with this system here. The system is this. That's your system right there. So the system, it's equal to M1 plus M2, okay? That's your system. So we're going to say when this is true, right? When this is true, if this net force is 0, then we can say conservation, the linear momentum, conservation of momentum. And this momentum is linear. So you can say conservation of linear momentum if you like. Okay, sometimes people don't say it. Conservation of momentum. What does that mean? So initially, right? So initially, the momentum is equal to M1 V1. plus m2 v2. Okay, so this is initially, and then they're going to hit each other. Okay, they're going to collide with each other. So then they're going to hit each other, and then they're going to actually bounce out, become a v1 prime going this way, and then become an m. So v2 prime going that way. Okay, but if this net force is equal to 0, then finally, right? So after collision means 碰撞. After collision of the two masses, then the PF is equal to m1 v1 prime plus m2 v2 prime. Okay. Now the conservation of momentum says the following. I'm going to change in color. Okay. So the conservation of momentum here says that these two are equal. So PI, it's equal to PF. Or you can then expand this one out and say m1 v1 plus m2 v2 is equal to m1 v1 prime plus m2 v2 prime. Be careful, this is vector, right? So this velocity is all vector here. They're all vector, okay? They are vectors. All right? So that is the conservation of momentum. I'm going to stop here, okay? Yeah. Hopefully you have learned something about momentum. We'll see you next time. Bye-bye now.